Hello everyone. Welcome to the last lecture of second week of our course. These 2 weeks, as we have already mentioned before, was more of introductory weeks of this course. In the first week, we talked about the basics of Earth observation. We talked about different sensors and discussion regarding the same continued to this week. Since then, starting from the second lecture of this week, we started discussing about machine learning paradigms that were popular before 2011 in Earth observation, or also we can say in computer vision as well. We started talking about supervised paradigms. We talked about support vector machine. We talked about decision tree. We talked about random forest. Now, in this lecture, we'll be talking about a few unsupervised paradigms. More specifically, we'll talk about clustering. We'll talk about a specific clustering algorithm. We'll talk about dimensionality reduction. And following this, we'll also briefly talk about unsupervised change detection. Indeed, change detection is one of the popular or most important problem area in Earth observation, and unsupervised change detection is often preferred compared to supervised change detection. This was even more true in the era before deep learning. Hence, we will spend some time discussing about unsupervised change detection. With this, let us start our discussion on unsupervised learning. Unsupervised learning aims to learn useful structures in the data. There is no supervision on inputs like x1, x2 up to xn. So let us try to understand from some non-technical examples. Think about, like, let us go back to our childhood, to our schooling, like primary school. Think about the sports day in the school. What used to happen? Like, let's say, there were 60 students in your class. And I'm not talking about like when actually the sports event is happening, but most of the other time in the day, entire day, you would probably be moving around in a few groups. These groups, let's say like fixed number of groups, let's say like 5 groups, okay, 60 students in 5 groups, maybe more, okay. They carry some meaning, right? Like they are not just random, okay. Like some 10 students or 12 students moving together, there is a coherence between them. So a similar idea also makes sense when you talk about data analysis, or machine learning. So examples of unsupervised learning include clustering, that is grouping similar inputs together and dissimilar ones far apart. Just now the example that I took, that in the sports day, all the students moving together in a few groups, this is more like something similar to clustering. Another important problem paradigm is dimensionality reduction, where the aim is to reduce the data dimensionality. Also, another problem statement is estimating the probability density of data, or understanding which distribution generated the data. So all these paradigms I'm talking at this point of time in the context of machine learning era before 2011, that is before the era of popularity of deep learning. However, even in the era of when deep learning became popular, we see that all of these are indeed still relevant. Clustering still corresponds to deep clustering, or understanding which distribution generated the data led to interesting paradigms in the era of deep learning, such as generative adversarial network and so on. So this is what I was talking about, right? Like this particular, this unsupervised learning, this, to be clear, is very important in the era of deep learning. Indeed, different forms of unsupervised learning, like self-supervised learning and so, they indeed allowed us to make significant progress that has led to the development of foundation models. In the later part of this course, we'll be talking about foundation models, and indeed the application of AI in various domains has been made popular, that it is right now like known to almost like everyone. That has become possible only thanks to the foundation models, or in a way like only thanks to self-supervised learning, which in a way is like a form of unsupervised learning. However, this is not the case that this is popular rather only in this particular era. This was also very important even in 2000s. Even in the 2000s, we see like this particular methods that we have just mentioned and we'll be studying in this class, in today's class, that they were also very important in 2000s. So here are a few examples, like unsupervised segmentation of remote sensing images. Given a remote sensing scene, there may be different classes, and it's not always possible that you will have like annotated data corresponding to these classes. So to get understanding of this remote sensing scene, it's often preferred that okay, you can actually segment the scene without using any unsupervised label. And this particular 2004 work that we have cited in the footnote in this particular slide, there the unsupervised segmentation of emotions in images is indeed used along with self-organizing map and k-means clustering. So talking about clustering, so we have already given like motivating example for clustering, right? So let us go a bit more deeper into clustering. Clustering is indeed one of the most popular unsupervised learning tasks. The goal is to divide given data into different groups or clusters such that the similar samples belong to the same cluster, whereas the dissimilar samples should belong to different clusters. Of course, it depends really on like how you define similarity and dissimilarity, which features you are using to compute the similarity and dissimilarity. The assumption, the very important assumption here is that no class labels are available. If we are using really indeed class labels, then it would have become a separate type of problem. So here our assumption is that, okay, we are not really using any class labels. K-means clustering is indeed one of the most popular clustering algorithm. Before going into actual K-means clustering, let us again discuss a non-technical example. So let me recall something from my own childhood, and I think like this would probably be similar to most of you. I don't know what's probably with the current generation, but this should be similar. I mean, this used to be very much with our own generation when we used to go to the field to play cricket, let's say. Okay, what used to happen is that let's say on a particular evening, we just ended up going to the field, and 11 or 12 or 15 odd persons of us gathered there, right? So all of us want to play. Some of us brought cricket bat, some of us brought cricket ball, but at the end, the main message is that okay, all of us want to play. So to play, the first thing we'll do is we will choose two captains. We'll randomly choose two captains. Let's say we'll choose, let's say, the person A and the person E. They are captains, okay? Now what happens is that, let's say the person B, C, D, they, when they found that, okay, this person A is the captain, the person B, C, D, they would say that, okay, we are kind of close to this person A, so we will join his or her team. On the other hand, let's say FGH, person FGH, they think that, okay, we are close to this person A, so we will join his or her team. Okay. So with this background, now what used to happen is that once this BCD has joined person A or person A's team, now often used to happen this person C who has also joined this person A's team, he or she has a more stronger personality. So automatically used to happen that, okay, if this person is in the same team, maybe this person is more meaningful as a captain. Okay, so somehow the captainship used to shift from person A to captain C. Similarly for the other team as well, right? And now when this captainship has shifted from person A to captain C, sometimes it used to happen that, let's say, this person B, who used to feel that, okay, he or she is indeed attracted to the leadership of person A, he or she is not anymore attracted to the leadership of person C. So he or she would then join the other team. So in this way, kind of a few iterations used to happen. And then, after a few iterations, the teams actually used to get stable. Then the actual match would happen, okay? So I'm not really interested about the actual match at this point of time. What I'm interested is just like this team formation phenomenon. So why I told this entire story, the K-means clustering, this kind of follows similar kind of principle or similar kind of algorithm. What happens is that in the first step, algorithm assigns every point to the nearest cluster center. So let's say we have a few cluster centers. The algorithm will assign all the points. Okay. So first of all, to have the cluster centers, of course, we need to have a fixed number of clusters and all. So let's say we have them. Given that, the algorithm will assign each point to the nearest cluster center. Then what happens in the step 2 is that we now change each of this cluster center, which in the example that we just discussed before is the reassignment of the captain, right? We said that the captainship shifted from A to C. So similarly, this cluster center, they gets moved to the average or the mean of the all assigned points. And now this process will keep on repeating. So now again, each point will get assigned to the nearest cluster center, and again we will get a new estimate of each cluster center. So let us see a bit more mathematically. Given, let's say, n unlabeled examples, which we can say like x1, x2, xn, each of them belonging to Rd, what we want to get is k partition or grouping of this data, right? So we have this n data points, each of them from d-dimensional real vector space, and we want to group them into k clusters. So to do this, first let us understand what are the desired outputs. There are two outputs. One is cluster assignment of all the n examples. So we have this n data points. All of these n data points will be assigned to one cluster, and since we are partitioning into k clusters in total, so we have k cluster means. So which mean like representing each cluster. So in our particular example from the cricket, it's like k captains, and each of the players, they are assigned to one of these captains. So of course, if you have this k cluster means, you can also derive yourself this cluster assignment of the n examples. So that is there. I mean, the desired outputs 2 is already enough, but I'm just for sake of completeness, we are mentioning these 2 different desired outputs. So how will you proceed? The first step, as we already mentioned in our example of cricket, what was the step there? To get a few captains, right? So similarly, we'll start with k cluster means here. Let's say they are mu1, mu2 up to mu k, and each of them again drawn from Rd. Let us assume for now that this mu1, mu2, mu k, they are indeed initialized randomly. There are other ways to initialize them instead of initializing randomly, and we'll actually briefly mention one of those methods. However, for now, let us just assume that they're initialized randomly. So with this, what happens is that, so those were those K cluster means, right? We want this K groups. Now what do we have? We have n data points in total, which means what we do, we'll assign each of these data points to the closest cluster that is given xn, will assign to the closest cluster, which can be computed by computing the argument of distance from different cluster centers. Now, in this way, of course, we got this Zn, this assignment of each of these points. Now let us recompute the means. That is similar to the, again, assigning a new captain, assignment of the captainship from person A to the person C in our example. So similar to this, in this case, particular case, we are recomputing the means Ck, which is, in this particular case, we are talking about a particular cluster and a means of all this point in that particular cluster. So one thing that probably needs to be briefly clarified is that, so when in the case of the cricket, the example that we took, we say that, okay, person A was the captain and person C became the captain. I mean, they are real persons. But in this case, it need not be, like a real, like a particular data point, right? This centroid, this need not be corresponding to a particular data point. Now, once we have computed this means, what we'll do is that if convergence is not reached, we will assign each point xn to the closest cluster and keep on repeating. So with this, the most obvious question that comes to our mind is that, what do we mean by convergence, or how do we understand that, okay, convergence has been reached, right? So if the convergence has not been reached, we said that, okay, like we will assign each of these data point to one of these clusters again, and we keep on repeating. But how do we say even that, okay, the convergence has been reached? There are like different ways which more or less like are similar to do so. So one is that the cluster assignments do not change. So between the previous iteration and between the current iteration, if the cluster assignments do not change so much, we can say that, okay, maybe we have reached convergence. Another very similar approach is that the centroids that are representative of different clusters, similar to, like if there were two teams and the two captains. So like, let's say like we are not playing with two teams, we are actually playing with 5 teams, let's say. So all these 5 captains, like they don't move, like we don't assign this captainship to different persons from one iteration to the other iteration. Similarly, in this case, the centroids, they do not move significantly. So we can say that in the case, probably we have reached convergence. Another way of defining convergence is also maximum number of iterations. So we say that, okay, we will keep on repeating this process for this number of iterations, and once this particular number of iterations it has been reached, we say that, okay, we have converged, no matter what, even if like the previous 2 conditions, they have not been met. So with this, we can indeed also write the k-means loss of the objective that it's trying to achieve. So this can be written in 2 different steps. So one with this small l, okay, so we see as a summation of small k is equal to 1 to k, zn k xn minus mu k norm square. Now, what we can do is we can go ahead and we can do this summation for all the n data points. So indeed, this particular equation can be written in slightly different ways, implying the same thing. What this at the end is representing is the within cluster sum of squares. And one important point to understand is that we are not actually directly optimizing this, rather we are using the alternating optimization, the k-means algorithm that we just described before. We are using this to implicitly achieve this optimization. Another important aspect here to understand is how to choose k, right? How to choose the number of clusters. Is it 2 number of teams in our cricket world? The example that we took, is it 3 number of teams? Is it 4 number of teams? Right? So there are again like different ways to do this. One very popular approach is like to actually plot the k-means objective versus k. Okay, so you take different values of k is equal to, let's say, 3, k is equal to 4, k is equal to 5, okay, number of clusters you vary, and accordingly you plot this k-means objective in the y-axis, and the plot that we'll see is something similar to this. Okay, so what we'll see is at some point there is a sharp, like change, or rather we call it this as elbow point. Okay, so looking at this elbow point, we actually can decide the number of clusters. So another very important aspect to keep in mind is that each iteration never increases the objective function. However, what can happen is that k-means can indeed converge to local optimum. And for this reason, initialization matters a lot in k-means. Poor initial centroid placement can cause the algorithm to get stuck in a poor local minimum. That's why there are like several solutions proposed in the literature. One possibility is this k-means plus plus, where the idea is to choose initial centroids that are far apart. The procedure goes like this: choose one centroid randomly, compute distance of every point to the nearest centroid, and points further away have higher probability of being selected as the next centroid. Okay, repeat until like the desired number of centroids are chosen. So let us see, like very quickly, a k-means example in Python. Again, k-means is conveniently available with scikit-learn. So we see in this particular example, we took 300 data points, and we took we generated the synthetic data in such a way that, okay, we have 3 data corresponding to 3 different distributions, and then we are indeed like applying the k-means to group it into 3 different classes. And eventually, when you plot this data, okay, we see this nicely, this 3 different classes here, and each of the centroid represented by the cross marks. So another important direction in unsupervised learning is dimensionality reduction. Again, a very important problem statement. We'll see like some of the areas where it's very crucial, like hyperspectral image analysis is one such case. And indeed, dimensionality reduction is also like often part of the, like the architecture of like deep architectures as well. So, okay, right now, of course, we're not talking about the deep architectures, but yeah, like this gives us the idea like how important dimensionality reduction is. High dimensional data often carries redundant information, correlated features, and comes with increased computational costs. So, with this, one dimensionality reduction approach that's very popular is principal component analysis. The question that we would like to ask at this point to us is that, can you represent the same data using fewer features while preserving most of the important information. And the answer to this is the PCA, which transforms the original features into a new coordinate system. The first principal component captures the maximum possible variance. Each subsequent component captures the maximum remaining variance while being orthogonal to the previous components. So how does it work? Given these data points x1, x2, xn, capital N, what we do is that we start with computing the mean, and then we subtract the mean from each data point. So we call this as data centering. So after the data centering has been done, let us assume that we have this centered data matrix, capital X, arranged as this n cross d matrix. So from this, what we do is that we compute a d cross d covariance matrix. Let's call this as S. Given this, on this particular matrix, what we'll do is we will do an eigen decomposition. Now, once the eigen decomposition has been done, we take this top k eigenvectors. Let's call them W1, W2, Wk. So we are getting this particular projection matrix, which is D cross K dimensional. Now, given a particular data point, x small n, its projection will be simply z small n, which is Wk transpose into xn. Now, let us spend a couple of minutes thinking about, a couple of practical examples. Let's say we are trying to do a monthly classification. Okay, so monthly classification, what do I mean? Given some data points, some multispectral images, some hyperspectral images, we want to for each month, we want to assign a particular class. Let's say this, for this particular month, we will say that, okay, this particular data point, which could be a pixel, which could be an image, let's say this belongs to water. For the next month, this belongs to something else, right? So now think of this we have the combination for this particular month. We have a combination of multispectral and hyperspectral images, which is quite possible, right? Let's say we have multispectral Sentinel-2 images taken every 5 days apart. So we have, let's say, 4 or 5 multispectral images. Let's say we have hyperspectral images. Let's say their improved resolution is 10 days. So we have, let's say, 2 or 3 of these hyperspectral images, right? So with this background, one question that probably you would like to ask yourself: will you do a PCA before going into further analysis? Maybe yes, right? Why? Yes. Multispectral images, probably they're let's say 4 channel or let's say 8 channel, something like that. Hyperspectral images, they're 200 channel. If you just first of all, okay, of course there are different number of acquisitions. There are, let's say, 5 acquisitions of multispectral, so let's say 4 channels each, so it becomes 20 channels. And then the hyperspectral images, let's say 200 channels each, and let's say there are 3 acquisitions, so this becomes 600 channels. So 600 and some 20 or 25 odd channels, I mean, it doesn't make sense, right? So probably we'll if you want to give similar kind of weightage to the multispectral and the hyperspectral information, probably we'll to bring the hyperspectral down to similar number of channels as the multispectral, right? So probably PCA will come into account, use there. Then of course you can ask yourself which classifier will you use? Will clustering be a possible approach here? So think about these questions. And these are there is no unique answer to these questions as such, but thinking about this will bring important or useful insight. So now, if we spend a few minutes discussing about unsupervised change detection. And the change detection is a very important paradigm in Earth observation, and we will later dedicate an entire week talking about change detection, where about 1 or 2 lectures are spent talking about unsupervised change detection. So now let us, form the background of this unsupervised change detection. So one of the most popular approach for unsupervised change detection in the era predating deep learning was change vector analysis. And indeed we see, when we'll talk about the deep learning based unsupervised change detection, the extension is pretty much derived from this change vector analysis called to deep change vector analysis. So this change vector analysis, this classical pixel-based change detection technique compared input bitemporal vectors. For each pixel, a change vector is computed as the difference between the input vectors acquired at the two dates. In the CVA, basically we compared the magnitude. Okay, so from this the difference we compute the magnitude, and this magnitude, this indicates the amount of the change, while a deduction can also be calculated, which provides an information about type of change. So the magnitude, let us restrict ourselves to this binary change detection, which is like distinguishing the unchanged pixels from the changed pixels. So there, the magnitude, on the top of magnitude, will apply a threshold to distinguish between the changed pixels and the unchanged pixels. So greater than this particular threshold, the magnitude is greater than this particular threshold, changed. The magnitude is less than this particular threshold, unchanged. Now, so what we say, this change vector analysis is done pixel wise, right? There are there were several approaches to improve upon this. One is possibility is this robust change vector analysis, where what was the concern is that okay, how to account for the possible misregistration between the images, because it's often quite common that okay, the pre-change image and the post-change image, they will not be perfectly registered, and when a pixel wise difference, this misregistration, even if it's just a couple of pixels, this may be disastrous. So what robust change vector analysis proposes is that instead of comparing only the corresponding pixels, we can rather instead compare a pixel with a local neighborhood in the second image, the post-change image. Similarly, another approach is indeed instead of thinking of this pixel wise changes, why not think object based change. Okay, and one possible very straightforward way to capture or to represent object in the pre-deep learning era was superpixel. Superpixel, this basically represents a homogeneous area, spectrally is homogeneous area in an image. So you take a particular superpixel, and let's say one possibility is that okay, for the superpixel you just let's say you are working with 4 channel images. So what you do is, or 3 channel images, you just take an average. Okay, or another possibility is, of course, you just compute some features from the superpixels, and then you take, instead of taking the difference between the original pixel wise spectral differences, you take a difference between these features computed from the superpixel. Now, another extension on the top of this is partial change vector analysis, which takes even this superpixel concept even further. So think, instead of a particular superpixel, think of it like a multi-scale information. Okay, so one possibility is that okay, the superpixels, you take the superpixels at the different scales. Okay, so you can think within one bigger superpixel you have the smaller superpixels. So these multi-scale units, which can be multi-scale superpixels, they capture the properties at different scales. Okay, so when representing a particular pixel, you don't just take this particular superpixel at one single scale, that property, you take the features from different scales. Okay, and you can concatenate them, and then you can just take the difference and then compute magnitude, just like in the change vector analysis. And this paradigm pretty much leads us, so why also I discuss this right now, this kind of pushes us towards kind of things that we'll be discussing later when we'll be talking about deep learning, not just for the change detection, also for semantic segmentation and many other problem statements. Indeed, multi-scale information is one very important aspect in image analysis. So with this, we'll stop here. From the next lecture or from the next week, we'll slowly start moving towards deep learning, CNN based architectures. So we'll stop here. Thank you.